Okay, today we will see what is this degeneracy. Degeneracy means there is a tie in selecting the outgoing variable. Degeneracy is said to occur in the following two cases. That is, at the initial stage, if the value of the basic variable is 0 in the initial basic feasible solution, or if the right hand side of the constraint has a 0 value. And the second case is at any subsequent iteration stage when there is a tie among the minimum non-negative replacement ratio. Whenever there is a tie, which means when in the ratio column, if two values are same, then we say there is a tie. In that case, earlier what we used to do, we used to randomly select any one variable, any one of the row as an outgoing variable. Okay, then when we select randomly, what will happen means it will result in the other type variable becoming 0 in the next stable, and the solution is set to degenerate. So there is in case of degeneracy, there is no guarantee that the value of the objective function will improve, since the new solution that is obtained will also remain degenerate. So here, to resolve the degeneracy, we will follow certain steps. That is, what we do initially means we pick up the rows for which the minimum ratio is same. Then we rearrange the columns so that the column that is forming the identity matrix will come first, and other columns, that is other decision variables, will come next. The third step is to find the minimum ratio. How to find the minimum ratio means divide the elements of the first column of identity matrix by the corresponding elements of key column. After dividing, there can be two cases. That is, the minimum ratio obtained, it can be a unique value. If a unique value is obtained, then we can determine the key element. Okay, if the minimum ratio obtained is not unique, okay, then what we do, we go on repeat the above procedure until we get the unique ratio. Then after resolving the degeneracy, a optimal solution to the given problem is obtained. So let us consider an example, okay, that is use degeneracy principles to solve the following LPP. Here we have an objective function z is equal to 3x1 plus 9x2, and the constraints we have x1 plus 4x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4, x1, x2 greater than or equal to 0. The first step is to represent the problem in a standard form. So after converting all the inequalities, we have x1 plus 4x2 plus s1 is equal to 8, x1 plus 2x2 plus s2 is equal to 4, and the objective function z is equal to 3x1 plus 9x2 plus 0s1 plus 0s2. And all these variables, that is x1, x2, s1, s2 should be greater than or equal to 0. And the next step is to find the initial basic feasible solution. So here we know that s1 and s2 is a basic variable, and x1 and x2 is the non-basic variables. If the value of x1 and x2 is 0, we have a value of s1 is 8, and for s2 it is 4. And the next step is initial table. Initial table, in the objective function we have x1, x2, s1 and s2, and the coefficient values. And for x1 the coefficient is 3, for x2 it is 9, for s1 it is 0, for s2 it is 0, and the basic variables are s1 and their respective coefficients are 0 and 0. In the first constraint, so this row represents the values that is present in the first constraint. In the first constraint, the x1 coefficient is 1, x2 it is 4, s1 it is 1, s2 0, and the right hand side of the constraint has a value 8. And the second constraint values are 1, 2, 0, 1, 4. Now how to find zj? 0 into 1 plus 0 into 1, we have a value 0. Again here also we have a value 0, 0, 0, 0. Again Cj minus Zj, that is 3 minus 0, 3, 9 minus 0, 9. Again 0 minus 0, 0, 0 minus 0, 0. Now, in Cj minus Zj, we have to consider a maximum value. So, 9 is the maximum here. Once we got a maximum value, this is our key column. This is our key column. As a key column, once you get a key column, we have to find out the ratio. How to find out the ratio? So we have to divide the values that is present in the solution column with the values that is present in the key column. So here we have 8 by 4, it is 2. Again 4 by 2, it is 2. Now you can see there is a tie. So we don't know which which row we have to select. So for that, what we do, there is a degeneracy. There is a tie, which means there is a degeneracy. To resolve this degeneracy, we apply certain degeneracy steps. Okay, so what is the first step means we have to rearrange the column. We know that S1 and S2 are the variables which are forming the identity matrix. Okay, this S1 and S2 column has to come first. So here I have rearranged the columns. S1 and S2 comes first, again X1 and X2. So here after rearranging all the columns, we have to fill all the values. Now as you can see, as I said, this x2 is our key column, right? Now x1 in this identity matrix, this is forming an identity matrix. So here we have a identity matrix 1 0, again 0 and 1. In the identity matrix, the first column is S1. So look at the values that is present in the S1. We have a value 1 and 0. And look at the values that is present in the key column. We have a value 4 and 2. So this value S1, that is 1 divided by 4, again 0 divided by 2, that is S1 divided by X2. So S1 value is 1, X2 value is 4, 1 by 4, again 0 by 2. 1 by 4 you will get a value 0.25, again 0 by 2 you will get a value 0. Both are unique values, 0.25 and 0, both are unique values. So among these two values, we have to pick a minimum one. So this is our minimum one. This is our minimum one. So after picking the minimum value, this will be our key row. This will be our key row. Now we know that S2 will be the outgoing variable and X2 will be the incoming variable in the next iteration. Suppose sometimes what happens means here in the first column, after dividing these values, that is first column values with key column values, we got a unique value. In some problems you may not get. In that case you have to consider the second column. When you don't get a unique value after dividing this first column value with the key column value, you have to go for the second column and pick the values that is present in the second column and divide that values with the key column values. Now here the key element, okay, 2 is the key element. We have to make this value as 1. So divide this entire row by 1. Sorry, we have to make this value, this key element is 2. We have to make this value as 1. So divide this entire key row by 2. So after dividing by 2, here we have a value 0, 1 by 2, 1 by 2, 1, 2. And this value, this 4, this has to be made as 0. How to make this as 0? R1 is equal to R1 is equal to R1 minus 4 times R2. So here I have performed the row operations. R1 is equal to R1 minus 4 times R2. So all these are the old values, the old values of R1, 10148. Again minus 4 times new values, 0, 1 by 2, 1 by 2, 1, 2. After performing the row operation, we have a value 1, minus 2, minus 1, 0, 0. Okay, substitute those values, 1, minus 2, minus 1, 0, 0. Now find the values of Zj. So Zj will be 0 into 1 plus 9 into 0. Here it is 0. Again 9 into 1 by 2, 9 by 2. Again here it is 9 by 2. Again here it is 9. Again optimal solution, 9 into 2 it is 18. Cj minus Zj, 0 minus 0, 0, 0 minus 9 by 2 minus 9 by 2, 3 minus 9 by 2 minus 3 by 2, 9 minus 9, 0. Now, if you see Cj minus Zj, all the values are either 0 or negative values. So, which is, it satisfy the optimality test, we have to stop here. So, here the optimal solution, Zj it is 18. The value of S1 is 0 and the value of X2 it is 2. Now you can see here, this is an example for degeneracy. Yes, right here the basic variable, okay, S1 is the basic variable which has a 0 value. S1 is a basic variable which has a 0 value. And now I told you, right, in case of degeneracy, the value of the objective function may improve or may not improve. In this case, the value of the objective function initially it is 0. Now in the iteration 1 it is 18. Okay, in this example, the value of the objective function, the value of the optimal solution, it has been improved. Now consider the second case. Okay, this is the second example where the maximum z is equal to 22, x1 plus 30, x2 plus 25, x3, and we have three constraints. All the constraints have an inequality type less than or equal to, so we have to add a slack variables. So in the first constraint we have added a slack variable s1, second constraint s2, third constraint s3. So initial we know S1, S2, S3 is the basic variables, and again X1, X2, X3 are non-basic variables. So if I set the value X1, X2, X3 as 0, we have a values S1 is 100, S2 is 100, S3 is 100. Now initial table. In the initial table we have to represent all the values. So now for the in the objective function we have all these variables. That is, we have x1, x2, x3, s1, s2, s3, and the value of x1 it is 22, value of x2 30, value of x3 25, s1 0, s2 0, s3 0, and basic variables are s1, s2, s3. S1 is 0, S2 is 0, and S3 is 0. And all these, okay, all these are the first constant values. Again, all these are the second constant values. Again, all these are the third constant values. Now we have to find the Zj. Zj. Okay, Zj, you will get all zeros. Okay, now Cj minus Zj will be 22, 30, 25, 0, 0, 0. So 30. Since this is a maximization problem, we have to consider a maximum value. So 30 is the maximum value. This is the key column. Now to find the ratio, we have to find the ratio, that is 100 by 2, 50, 100 by 1, 100, 100 by 2, 50. So here again, here there is a tie. Yes, right. Here we have two values, two same values, 50 and 50. So among all these three values, 50 is the minimum. Whether we have to choose this row or we have to choose this row, there is a degeneracy. So to resolve degeneracy, use the degeneracy rules. So which is the identity matrix? Which are the columns forming the identity matrix here? S1, S2, S3. So they are forming the identity matrix. So um, So here, the which is the first column in the identity matrix? S1. So divide. Okay, so divide the values, the values that is present in S1 row, those values we have to divide it by the key column values. So here we have two rows. Okay, only two rows. Only in the two rows we have same values, that is in the first row and the third row. So we have to consider only those two rows. So here S1 value is 1. Again, in the first row it is 1. In the third row it is 0. So 1 divided by 2, it is 0 0.5. Again, 0 divided by 2, it is 0. So which is minimum? 0 0.5 is minimum or 0 is minimum? 0 is minimum. So we have to consider this third row as our key row. So now this is our key row. So S3 is the outgoing variable, X2 is the incoming variable. So in the next iteration, this is 2 is the key element. In this value, we have to make it as 1. We have to divide the entire row by 2. So after dividing by 2, we have values 1 by 2, 1, 1, 0, 0, 1 by 2, 50. I told, right, S3 is the leaving variable and X2 is the entering variable. So X2 coefficient is 30 and S1, S2 coefficients are 0, 0. Now, now we have to make this as, this value has to be made as 0. Again, this value we need to make it as 1. So this we have done it as 1, okay, by dividing the entire row by 2. Now, how to make this as 0? So R2 is equal to R2 minus R3. Okay, how to make this as 0 means here we have 1, yes, right? So that is why R2 is equal to R2 minus R3. How to make this value as 0? R1 is equal to R1 minus 2 times R3. So after performing the row operations, we have a values. So after performing the row operations, here we have all these values. Okay, now I have performed all the row operations below. You can check. Okay, now we have all these values. Now we have to find the zj values. Okay, zj, okay, that is z1 value will be 50, z2 30, z3 30, z4 0, z5 0, z6 15, and the solution, okay, the solution obtained, it is 1500. Cj minus zj. Cj minus Zj, here we have 7, 0, minus 5, 0, 0, minus 15. So among all these values, 7 is maximum. So this is our key column. So how to find a key row? We have to find a ratio. That is 0 by 1, 0, 50 by 3 by 2, 100 by 3, 50 by 1 by 2, 100. Among these values, 0 is the minimum one. So we got a key row. Now, 1 is the key element. Our main goal is to make the value of key element as 1. So this is already 1. We don't have to do anything. Okay, these values will remain same in the next iteration. 1, 0, minus 2, 1, 0, minus 1, 0. And this 3 by 2 and 1 by 2, we make it as 0. To make it as 0, we have to perform row operations. What is the row operation? Means R2. R2 is equal to R2 minus 3 by 2 times R1. Again, R3 is equal to R3 minus 1 by 2 times R1. After performing the row operations, so after performing all the row operations, we will have these values. We will have these values. Okay, here down I have performed the row operations. We will have those values. Now in this iteration, okay, in this iteration we have to find a zj values. Okay, zj will be So these are the zj values. It is 22, 30, minus 16, 37, 0, 8. Again here the optimal solution, it is 1500. See, even in the previous iteration the solution is 1500. Here also it is 1500. Okay, why? Because of degeneracy. Okay, whenever there is a degeneracy, the solution obtained in the next iteration may be same as previous iteration. It can be same, or it may sometimes it may improve, or it can be same. So now here in Cj minus Zj, in Cj minus Zj we have value 0, 0, 9, minus 37, 0, minus 8. So 9 is the maximum one. So this will be our key column. Now key row, here 0 minus 0 divided by minus 2, 50 by 3, 50 by 2. See here we have a minus 2. Even though this 0 it is minimum, here we have a negative value. We cannot consider this as our key row. Okay, so we have to pick any one in these two values, 50 by 3, 50 by 2. So 50 by 3, it will be the minimum one. So this is our key row. In the next iteration, x3 is the entering variable and s2 is the leaving variable. And again here we have one value, this 9 is maximum. Okay, this 9 is maximum. We need to go to the next iteration. So in the next iteration, I told you, right, in the next iteration, so x3 is the entering variable and this value we need to make it as 1. So we have to divide this entire row by 3. After, okay, we have to divide this entire row by 3. Now here we have a value 0, 0, 1, minus 1 by 2, 1 by 3, 1 by 3, 50 by 3. And other values it is present in the key column should be made as 0. These values we need to make it as 0. So in the how to make this first one as 0 means R1 is equal to R1 plus 2 times R2. Okay, how to make this as 0 means R1 is equal to R1 plus 2 times R2. How to make this as 0? R3 is equal to R3 minus 2 times R2. So here I have performed all the operations. Here I have performed all the operations. So after performing all the operations, all the row operation, we will fill all the values. Again, Zj values will be, we have to compute Zj values and Cj minus Zj values. Now here, if you observe here, all the values that is present in Cj minus Zj is either negative or 0 values. And the optimal solution Zj is 1650. So here there is an improvement in the optimal solution. So the optimal solution is 1650 and the value of x1 is 100 by 3, x3 it is 50 by 3, x2 it is 50 by 3. And we will see the next problem. Okay, the next problem, okay, we have z is equal to 107 x1 x plus x2 plus 2 x3, constraints 14 x1 plus x2 minus 6 x3 plus 3 x4 is equal to 7. Again 16 x1 plus 1 by 2 x2 minus 6 x3 less than or equal to 5, 3 x1 minus x2 minus x3 less than or equal to 0. Here we have three constraints. So the first constraint as a equality type and other two constraints has a inequality type. Okay, here if you observe all the constraints, okay, you just look into the variables that are present in all the constraints. See, this x1, x2, x3 is present in all these three constraints. X1, x2, x3 variables are present in all the three constraints. So this x4 variable is not present in the second constraint and also in the third constraint. So here we can treat this x4 as a slack variable, but we know that for a slack variable the coefficient value should be 1. So how to make it as 1 means we have to divide this entire constraint by 3. So after dividing it by 3, here we have 14 by 3 x1 plus 1 by 3 x2 minus 2 x3 plus x4 is equal to 7 by 3. And the second and third constraint, we have a inequality type less than or equal to, which means we have to add a slack variable. So we have added the slack variable S1, S2 and the initial basic feasible solution. So here the basic variables are x4, S1, S2. Okay, if I set all other non-basic variables as 0, we have a value for x4 it is 7 by 3, S1 it is 5, S2 it is 0. And finally, if I substitute all these values in the objective function, we will have the value for z as 0. So z as 0. So from 0, we will start. So 0 will be our initial feasible solution. Now we will see whether we can improve our optimal solution or not. Now, so in the objective function, we have a variables x1, x2, x3, x4, s1, s2. For x1, coefficient is 107, x2, 1, x3, 0, x4, s1, s2. All these are basic, it is 0. Here also all these are basic variables, it is 0. And all these are the values that is present in three constants, 14 by 3, 1 by 3, minus 2, 1, 0, 0, 7 by 3. Second constant has a values. For x1 it is 16, for x2 1 by 2, x3 minus 6, x4 0, s1 1, s2 0. Right hand side of the constant has a value 5. And the third constant has a value. For x1 it is 3, x2 it is minus 1, x3 minus 1, x4 0, s1 0, s2 1. Right hand side it is 0. Now zj we will get all zeros. Again cj minus zj we have these values. Okay, now among all these values we have to consider a maximum one. So this is our maximum one. So now x1 will be our key column. Now we have to find out the ratio, that is 7 by 3 divided by 14 by 3, 1 by 2. Again 5 by 16, again 0 by 3, it is 0. Among these three values, this is the minimum. So S2 will be the key row. S2 row will be the key row. In the next iteration, X1 is the entering variable and X2 is the leaving variable. And this 3, okay, and this 3, this is the key element, this 3 is the key element, we need to make it as 1. To make it as 1, to make this value as 1, we have to divide this entire row by 3. After dividing, this value will become 1. Now we have to make these two values as 0. So these two values should be made as 0 and this should be made as 1. So now how to make this as a 0 means R2 is equal to R2 minus 16 times R3. How to make this as 0 means R1 is equal to R1 minus 14 by 3 times R3. So now after doing all the row operations, row operations, we have all these values. Okay, these are the values obtained after performing row operations. Now we have to find out Zj and Cj minus Zj. So after computing Cj minus Zj, we have a value 113 by 3. Okay, we have a value 0, 110 by 3, 113 by 3, 0, 0, minus 107 by 3. Again, this is a maximization problem. We have to consider a maximum value. So this is the maximum value. So X3 is our key column. X3 is our key column. Now we have to find a key row. So here 7 by 3, here see if you observe here all the values are negative. Okay, so here we will get all negative values. In the ratio column, we should always pick a minimum positive value. We cannot choose a negative value and a infinity. So here it is not possible to determine a key row, which means it is not possible to determine a outgoing variable. Hence, this problem has no solution, or we can say that this problem has an unbounded solution. So the next example, Next example, here you can see both the constraints have equals. Okay, both the constraints have equals. So whenever the in the given problem, if there is a equals, okay, then equality type, then you first see what are the variables that are present in both the constraints. So in first constraint we have x1 and x3. Okay, in second constraint we have x2 and x3. So if you observe, this x1 constant is present only in the first constant and it is not present in the second constant. So we can treat this x1 as slack variable. And if you observe the second constant, x2 is present only in the second constant and it is not present in the first constant. So x2 can be treated as a slack variable in the second constant. So if S1 and X1 and X2 are the slack variables, so we have to find the initial basic feasible solution. I told, right, X1 and X2 are the can be treated as slack variables, which means they are the basic variables. So only non-basic variable is X3. If I set that value as 0, we will obtain a value for X1. Okay, if I set this X3 as 0, X1 will be 0 and X2 will be 1. So if after substituting the values, x1 values, x2 values and x3 values in the objective function, so I told you, right, x3 is a non-basic variable, its value is 0, and x1, okay, and x1 value, okay, x1 value it is 0, again x2 value it is 1. So after substituting all these values in the objective function, for objective function we will have a value z is equal to 3. So we will start our initial solution from 3. So 3 is the starting solution. From that solution, we will check whether we can obtain a better solution than this. Now, so we have to represent all the values in the initial table. I told you, right, in the objective function we have x1, x2, x3 and the coefficients are 2, 3, 10. Basic variables are x1 and x2 and the coefficient values are 2 and 3. All these are the first constant values. For x1, in the first constant for x1 the coefficient is 1, x2 it is 0, x3 it is 2. Right hand side has a 0 value. In the second constraint for x1 it is 0, x2 it is 1, x3 1, right hand side 1. So zj, we have to find the zj. Zj 2 into 1 plus 3 into 0, we will get 2. In the same way we have to find other values. So 3, 7 and the optimal solution it is 3. Now cj minus zj, cj minus zj, here 2 minus 2 0, 3 minus 3 0, 10 minus 7 3. Now 3 is the maximum value. So x3 will be our key column. X3 will be our key column. Now ratio 0 by 2, again 1 by 1, 0, 1. So this is the minimum one. So x3 is the key column and x1 is the key row, 2 is the key element. We need to make this value as 1. So how to make this value as 1? We have to divide this entire row by 2. So after dividing this entire row by 2, we have a values 1 by 2, 0, 1, 0. Again, we have to make this value as a 0. How to make this value as 0? R2 is equal to R2 minus R1. R2 is equal to R2 minus R1. So now we will have a values minus 1 for second row, minus 1 by 2, 1, 0, 1. Again, After computing Zj and Cj minus Zj, for Cj minus Zj, we have values minus 3 by 2, 0, 0. So all the values are either 0 or negative. We have to stop here. So this Zj is 3. This is the optimal solution. See here, if you look into this example, this is also an example for degeneracy. We actually started from the initial solution 3. Okay, in the initial table also we have a same value. Okay, there is no improvement in the objective function. Again, in the final table also we have a same value 3. So there is no improvement. Again, here if you look, the basic variable, the basic variable is also 0. So here the value of basic variable x1, it is 0. Even at the end of the, even in the last iteration, okay, even in the end of the last iteration, the basic variable x3, it is 0. So for this, the solution, whatever the solution that is obtained here, it is degenerate. The basic variable x3 has a 0 value, and the value of z is same in both initial table as well as in the iteration 1 table. Thus, we have obtained the optimal degenerate solution from a degenerate solution without improving the value of z. See here, whenever we have a equal sign, okay, we will check whether we can treat any one of the variable as a slack variable. If it is possible, we can treat any one of the variable as a slack variable and we can continue the simplex method. Suppose in certain problems it is not possible to treat any one of the variable as a slack variable. Okay, in that case what we do means, we usually, if it is of equality type, then we usually add the artificial variable. Say artificial variable will be, suppose say here we have x1, here we have x2, here we have x1, right? Suppose in this so suppose if this problem in, so if I alter this question, okay, suppose assume that we have this type of constant, okay, x2, x1, 2, x3, x1, x2, x3. If this is the case, then here we cannot treat any of the variable as a slack variable, because all the variables, okay, x1, x2, x3, it is available in first constant. Again, x1, x2, x3, it is available in second constant. In that case, what we do, we usually add a artificial variable. Okay, here what we do, we usually add a artificial variable. And whenever we had an artificial variable, the usual simplex method is not suitable. The given problem has to be solved either by using big M method, or we have to solve it by using two-phase method. Okay, we will look into the problem and we will solve it by using any one of these two methods.